Hi, I'm Chris Wood. I'm a senior research scientist at IBM Quantum, and today I'm going to be talking about the Qiskit Runtime Primitives version 2 that was recently released, and how you can use this to run quantum computations on IBM's devices. So the Qiskit Runtime is essentially a containerized cloud execution environment for performing high-performance quantum computations. So its main feature is to enable the ability to run quantum programs in an environment where the classical computer is physically closer to the quantum computer, and the interface for doing this is through the runtime primitives, which I'm going to discuss. The primitives are a foundational building block for quantum programs designed around optimizing the execution of quantum workloads. They provide options to customize the iteration and execution of programs to maximize the quality you can get from running on IBM quantum processors. So there are two quantum primitives that we use when running quantum computations, the sampler primitive and the estimator primitive, and I'm going to cover both in this lecture. So the sampler primitive is a low-level execution primitive where we care about extracting the measurement outcomes of quantum circuits, and it returns single-shot measurement outcomes. So the circuits that are run on the sampler should include measurements to return these outcomes for. The estimator primitive, on the other hand, is a higher-level abstraction for running quantum circuits where we care about the expectation values of operators. So since this returns expectation values, the circuit does not need to contain measurements, since we're going to be adding measurements to that to compute these. With the release of Qiskit 1.0, we introduced a new version of the runtime primitives, version 2. So I'm going to be discussing those in this lecture. Now, the main change in the version 2 primitives over version 1 was to allow more efficient specification and execution of parametric programs. In particular, the implementation of the primitives for our hardware in the Qiskit IBM runtime was introduced in version 0.21. And this is designed to allow built-in support of error suppression and error mitigation techniques used for utility-scale workflows. So I'll start with the sampler primitive. So the sampler v2 primitive, as I already mentioned, is intended for low-level workflows. So it's designed for the execution of circuits and returning the measurement outcomes from those. The API for the new sampler primitives is shown here. So it has a run method, and any implementation of a sampler must implement a run method like this. It accepts a form of quantum payloads in something that's known as a primitive unified block, or a pub, and optionally you can also specify a number of shots that you would like to run each of these pubs for. So this input can select one or more pubs to run, and they'll all be run together in a single job. And the shots is optional. If you don't specify it, then the shots will be chosen by the sampler primitive itself. Now, primitive unified blocks were newly introduced with version 2, and they're designed to handle these parametric quantum circuits. So a primitive unified block is essentially a program structure for a sampler. It can be thought of as a tuple of three objects: a quantum circuit, which specifies the circuit that we want to execute, containing measurements; an optional set of parameter values that, if the circuit's parameterized, will evaluate it many times for each different set of input parameters; and optionally it contains shots to allow the execution of different shots for different circuits if you're running multiple circuits in multiple pubs. Now, the restriction of these arguments in the sampler are that the circuit has to be what's called an ISA quantum circuit, and it needs to contain at least a classical register and measure instructions on that register so it has some output to return. The parameter values that you specify in a pubs are essentially an array of float values to assign to all the parameters in the circuit. And in general, this can be a tensor-shaped array if we want to run many different sets of parameters on our circuit for a given workload. The optional shots argument allows us to specify within the pub itself the number of samples we want to draw from the sampler. So essentially the number of times we execute each set of parameters on the given circuit. Now, when you're running with these, there's various ways you can represent the pub, and we call these pub-like inputs. Because some of these values are optional, you don't always have to include them, and I'll show various ways you can specify a pub for running on the new sampler primitive. So the first way is the parametric circuit, and this is the tuple described above, where you pass in a parametric quantum circuit, the parameter values, and the shots you would like to run with. Now, you don't have to include shots in this specification, and if you don't, they can either be provided in the run method or by the primitive itself, and in this case, a sampler pub that is valid is just a parametric circuit and the parameter values. Now, we also want to allow executing non-parametric circuits through this interface, and in this case, a valid pub is a non-parametric circuit. Since it's non-parametric, there are no parameter values to run it with, and we can also specify the shots or leave the shots up to the sampler. Now, this last case of just a single non-parametric circuit is similar to the previous version 1 sampler, or just using the original backend.run. Now I'll go through a quick example of what this might look like if you're using the sampler. So for this example, we'll consider a simple 2-qubit Bell state where we prepare an entangled state on 2 qubits and perform a measurement. So the first thing I do is load my IBM runtime service, load my account with a saved API token, and select the backend I'd like to run on. For this example, I'm running on IBM Auckland. So the next thing I do is use Qiskit to create a quantum circuit. In this case, it's a 2-qubit circuit with a Hadamard gate and a controlled NOT gate, and then measuring both qubits. Now, because samplers require ISA circuits, which I'll cover a bit more in a few slides, I have to transpile this circuit to my intended backend to make it an ISA circuit. And then I can construct a simple pub for this non-parametric case. Now, to run this on the sampler, I import the sampler from the IBM runtime, initialize it for my chosen backend, and then run this pub. In this case, I ran it for 10 shots using the sampler run method to specify the shots. And then I can, from the job I get from this, I can extract the measurement result and look at the outcomes. The sampler job run on a sampler v2 will contain a primitive result that has an ordered list of the pub results for each of the input pubs that we ran. So if we run a single pub, this list will be a length 1 list containing a single pub result. If we ran with 10 pubs in the run call, it would be a length 10 list with 10 pub results. A pub result is a container class that contains all the data from the measurement outcomes as well as any optional metadata that may have been added by the primitive. And these can be accessed by 2 attributes: the data attribute, which returns the data structure containing the measurement results, and the metadata attribute that returns a dictionary of any optional metadata added by the primitive. Now, the data container is a special class called a data bin that was introduced in Qiskit 1.0. The data bin can store the measurement outcomes from the sampler. So if we ran with a circuit with 1 or more classical registers, then the data bin will contain fields and attributes with the same name as the name of the classical registers run, and their value will be the measurement outcomes for those measurements. And when working with a data bin, you can access these either by attributes using the register name or as a mapping using the name as a field. Each of these measurement outcomes is also a special data structure called a bit array. Now I'll go a bit over the bit arrays and how you can work with these. So to access the measurement data in one of these pub results, you'll get a bit array for each individual classical register in your circuit. And the bit array stores the single shot measurement outcomes for the number of shots we ran for that circuit. So that might look like this. I can get the measurement data, extract the bits. In this case, there was a single classical register named mesh, and it has a variety of attributes I can use to access information about the measurements outcomes. So you can think of a bit array as being an ND array-like object, like a NumPy array, with the following attributes. It has a shape, and that shape is given by the input pub parameter shapes. So if we ran 1 set of parameters, it would be shape 1. If we ran 10 set of parameters, it would be shape 10. It contains the number of bits that were run on that register. So in this case, it was a 2-bit register that I measured my outcomes into. It records the number of shots for the execution we ran. In this case, the number of shots was 10. And then there's also an array that stores the measurement outcomes on all the bits. And now, to get a little bit into the details, the internal structure of this array, for efficiency, stores the measurement outcomes as a packed array of bytes, or 8-bit integers. So for my example here of a Bell state with 2 measurement outcomes, which in the ideal case are both 0, 0 or 1, 1, represented as a byte array, these are stored as values 0 and 1. Now, if you're used to working with the previous counts formats of backends, there are helper methods on this bit array class to allow you to convert into these string methods. So the get bit strings example on the bit array can be called to convert these bytes into bit strings for each of the shots. And there's also a get counts method to return this in a counts dictionary format like shown. As previously mentioned, when you run on a sampler, the circuits have to be something known as an ISA circuit. So now I'm going to go over what an ISA circuit actually is. So an ISA circuit is a quantum circuit object in Qiskit which satisfies the following properties. It has to have the same number of qubits as the device it's going to be run on. It has to only contain allowed gate instructions that are supported by the device it's going to run on. And along with this, it has to satisfy the connectivity of the device it's going to run on. So if a device supports controlled NOT gates, it can only be controlled NOT gates on qubits that are allowed to be coupled by these. So if you're used to working with abstract quantum circuits and running them, to convert an abstract or logical quantum circuit to an ISA circuit, in Qiskit this is done via transpilation of the circuit to the intended target or backend. So for an example, if I took the 2-qubit Bell state as shown here with 2 qubits, 2 CL bits, and I wanted to transpile it to the IBM Auckland backend I used for my example, this is a 27-qubit backend, and the output might look like something like this. The circuit has been transpiled to the native basis gates for this device, which is a square root X gate, RZ rotation, and C NOT gate, and it's been expanded with ancilla qubits to be a 27-qubit for this device. Now, as I mentioned, the new V2 primitives are heavily optimized to work with parametric workloads. So now I'll just recap what a parametric circuit is. So a parametric circuit, either an ISA circuit or an abstract or logical circuit, is a quantum circuit that contains unbound parameter values that we may wish to evaluate for a variety of different values. So to take our previous example and to make it parameterized, I could control the initial single qubit rotation via parameter, which would also control the amount of entanglement that is generated. So I've modified it in this example to be a controlled Y rotation by an angle theta rather than a Hadamard gate. So when running a parametric circuit, the shape of the parameter values controls the shape of the input pub and also the shape of the pub results. So essentially, if you think of the parameter values as an array or a tensor, the shape of this array controls the shape of both the pub and the results. If I had a non-parametric circuit, then this would be equivalent to a trivial shape, which is specified as shape of the empty tuple, the same as in NumPy. If I ran an ISA circuit with k parameters and I wanted to run n different sets of these k parameters, that input array I would run in my pub has a shape nk, but the shape of the pub and the shape of the pub result is actually going to be a one-dimensional array of shape n. And you can always think of a parametric pub as being converted into a list of non-parametric pubs by binding all the parameter values. And this would be how things were run in the previous version of the primitives. So to go back to our previous example and show how this is run on a primitive using a parametric pub, I'll take my 2-qubit circuit with a theta angle specifying the degree of rotation to generate entanglement. And I can generate a set of parameter values I want to evaluate for theta. So using NumPy, I made a linearly spaced set of parameter values from 0 to pi with 20 different values. Again, I can transpile my circuit to make an ISA circuit for this on the back end I'm intending to run on. And then I can produce my pub, which now contains the circuit and the array of parameter values. Now this pub will have shape 20 because there's 20 different values of the single parameter I wish to run. So running this for 1,000 shots and getting the results, I'll get back a bit array for my measurement register now that has shape 20 and 1,000 shots. So for each of these 20 different theta values, I get back 1,000 shots of measurement outcomes. And so using that, I can plot the results versus the parameter theta. So using MATLAB here, I'll get my bit array and basically compute the probability of the state being 0, 0, or the probability of the state being 1, 1 by comparing the values of the bit array that is 0 or 3 and taking that sum and normalizing it by the number of shots. And plotting that, I can see something like this where starting from 0, my state is entirely in 0, 0. As theta approaches pi on 2, I get to a state of maximal entanglement where the state is 50% 0, 0, 50% 0, 1, 1. And at an angle of theta equals pi, now the state is almost entirely in 1, 1. So as I mentioned, there's various ways to specify shots when running on a sampler. So I'm going to go over them now. So you can specify shots either in the pub itself, in the run call, or you could just leave them absent and leave it up to the sampler. And depending on how you do that, there's a heuristic for the resolution of the shot values when you do the execution. So if shots is specified in the pub, this will take precedence and be used. So for example, if I took 2 pubs here, both with the same circuit, one I wanted to run for 100 shots, and one I wanted to run for 200 shots, and I called the sampler now with 1,000 shots like this, you can see that in the outcome, the pub results, one only has 100 shots and one has 200 shots. So essentially, the shots argument of the run call has been ignored because both pubs specified the shots themselves. Now, the second case where I use the shots argument, this will be used for any of the input pubs that don't specify the shots. So now to modify this, I'll remove the shot values from the first pub so it doesn't specify the shots it wants to run in, while the second one still specifies 200 shots. And running now, I can see that the first pub was run with 1,000 shots, while the second one was run with 200 shots. And the final case, that is if shots isn't specified in the run call and isn't specified in the pub, then the sampler has to have a default value for the number of shots, and it's up for the sampler to decide what this will be, depending on the implementation of the sampler. So to do this, the second example again, now removing the shots keyword arg from the run call, I can see that the first pub that didn't specify shots was run for 4,096 samples, while the second one was run for 200. And this was run on the IBM runtime sampler, and that's because the sampler in the IBM runtime chooses a default value of shots for 4,096. Okay, now we've given a quick overview of the new V2 interface of the sampler and its inputs and outputs. I'll move on to the estimator. So just to recap, the estimator primitive is a higher level primitive than the sampler, intended for computing expectation values on the final state of a circuit. The estimator API looks similar to the sampler API, where it can accept a list of pubs for input. However, these are estimator pubs, not sampler pubs. And instead of shots, the run argument for specifying the runtime is given by a precision argument. So like the sampler, it can accept one or more pubs as its input program. And the optional precision argument essentially expresses the desired precision we want to evaluate the expectation value to. So the primitive unified blocks or pubs for the estimator are a little different than for the sampler pub, because now we need to give a specification of the observables we want to compute the expectation values for. In this case, it's given by a tuple now that has 4 elements. The first one, again, is an ISA circuit, like with the sampler. However, the second one now is a list of observables we wish to evaluate on the pub. And then we have the optional parameter values and the optional precision. So like with sampler, because some of these values are optional, there's a variety of different pub-like inputs that are valid to give to the estimator. So the first one, where everything is specified, is a parametric ISA circuit to evaluate expectation values on, an array of observables that must be ISA observables for that circuit, then an array of parameter values, and a target precision. Now, I could drop the precision and I could do a tuple of 3 elements of just the circuit, observables, and parameter values. And then I can also consider running non-parametric circuits where I don't need to specify the parameter values, but I still need to specify the non-parametric circuit and observables and precision, or just the non-parametric circuit and then the observables, and leave the precision as the default value. So now, when working with estimator, we need to talk about how we represent observables that we wish to measure on circuits. So first, to go over what an observable is, it is a Hermitian operator that is represented as a linear combination of Pauli operators in Qiskit. So a single Pauli operator is an observable, and you can represent these either as a string that contains an I, X, Y, or Z terms to represent an n-qubit Pauli, or you can use the built-in operator objects in the Qiskit quantum info module, such as the Pauli object. For representing an array of observables, we can use a list of Pauli operators. This can be done by either passing in a Python list of Paulis or using one of the quantum info objects, such as a Pauli list, which represents a list of Paulis. Now, a more complicated observable, such as a Hamiltonian or another Hermitian operator, can be represented using the sparse Pauli op, which allows you to represent an operator as a linear combination of Paulis with coefficients. And for it to be a Hermitian operator, the coefficients must be real. So to give an example of this, I'm going to go back to my Bell circuit example, create an ISA circuit for the estimator. Note here that I removed the measurement from the circuit, unlike the sampler, because the measurement is going to be done by the estimator itself. So I create a Bell circuit without measurement, just with a Hadamard gate and a controlled NOT gate, and then I transpile it for my backend. And now if I wish to evaluate a ZZ observable, I can create this with a sparse Pauli op. And now to convert this into an ISA observable on my backend, which is a 27-qubit observable, I can use the apply layout method of the sparse polyop to map it to the same qubits that the transpiler mapped the circuit to. And this is done by using the layout of the transpiled circuit. Now, the result when running on an estimator will also be a primitive result containing a list of pub results, just like the sampler. However, the difference now is that the data bin that is returned by an estimator doesn't contain measurement outcomes from classical registers. It instead contains two fields to return the expectation values. There's an EVs field, which returns the mean estimated expectation values for all the requested circuits and parameter values. And there's a standards field that returns the standard error of the mean of the expectation value estimates. So for my example, if I take an estimator on my IBM Auckland backend, generate a pub with the ISA circuit and ISA observable and run it, because this was a non-parametric circuit with a single observable, I get back a single float value for my expectation value, and standard error is shown here. So like the sampler, the estimator pub and results both have a shape. However, this doesn't just depend on the parameter values like it did in the sampler case. For an estimator, the shape depends on both the parameter values and the observables. So first I'll go over trivial shape pubs. Now, like with the sampler, these have a shape given by the empty tuple, and in these cases, the return of the expectation value will be a float. Now, examples that can have this trivial shape are a non-parametric pub evaluated with a single observable, so no parameter values. But you can also have a parametric pub with a single parameter value and a single observable that will return a single float. Now, in the general case, where both the observables and parameter values can be tensors or ND arrays, then the shape will depend on what's called the broadcasted shape of these two tensors. So broadcasting is a concept from NumPy for combining two n-dimensional array objects into a larger array, where the dimension of the final array depends on the dimensions of the two components that are broadcasted. And the dimension of these arrays have to satisfy certain rules to be compatible with broadcasting. So the two arrays do not need to have the same number of dimensions, but their dimensions do have to satisfy certain properties. If they don't have the same dimension, the resulting broadcasted array will have the same number of dimensions as the largest of the input arrays. And each of the dimensions is going to be the largest size of the corresponding dimensions of the two arrays being broadcast. And any missing dimensions are essentially padded and assumed to have size of 1. And when padding, this starts with the rightmost dimension and works its way left. So if I had an array with 3 dimensions, an array with 2, the array with 2 dimensions would have a 1 added on the left to make it a 3-dimensional array. And then when doing this with 2 arrays, they're compatible to be broadcasted, where once you've padded them to be the same shape, then either all the dimensions are equal or one of the arrays has to have dimension 1 for that axis. Now, this is much easier shown with an example. So if I take 2 arrays here, say a matrix or 2D array A with shape 5 by 4, and then a 1D or vector array B with shape 1, the result here would be a 2D matrix with shape 5 by 4, because the array B would be padded with an extra dimension of 1 on the first, and then because they're both 1, the shape would come from A. Now, to take a bigger example, if I did a 3D array, A with shape 15 by 3 by 5, and B with shape 15 by 1 by 5, again, the result would be 15 by 3 by 5. Now, to look at this with pictures, if I think about broadcasting the parameter value sets and the observable array and what the resulting shape of the expectation values we could get for the sampler would be. So the trivial case, which I mentioned, is just one set of parameter values. So this has shape of the empty tuple, and a single observable in the observables array. This also is an empty tuple, and that will give me a single float or shape trivial expectation value estimate. Now, if I consider broadcasting a single set of observables, I could again have either an unparameterized circuit or a parametric circuit with a single set of parameter values, and now an array given by a 1D list of observables with shape 5, and I would get back a 1D array of shape 5 of the final expectation values, where in this case, the circuit will be run 5 times with that set of parameters to estimate the expectation value of each observable for that set of parameters. Flipping this around, I could have had 5 different sets of parameter values, each that I want to run with a single observable, and that would be a shape5 result where I estimate the same observable for each of the different sets of parameter values. And now to go to more advanced types, I can use this broadcasting to compute both inner and outer products of observables. So for example, if both my parameter value sets and observables were a list of shape5, the resulting expectation value would also have shape5 where the first set of parameters is evaluated with the first observable, the second set of parameters with the second observable, and so on. By padding dimensions, I can also do an outer product. So if I added a dimension of 1 to the start of the parameter value sets and added a dimension of 1 to the end of the observables, as shown here, I can produce a matrix of outputs of, in this case, 6 different parameter sets of input and 4 different observables, where I evaluate each of the 6 parameter values with each of the 4 observables to return this 4x6 array of expectation values. And then, of course, this can generalize to higher dimensions using the NumPy broadcasting rules, as shown here. So this is maybe easier given with an example. So if I go back to the Bell example and now consider the parametric Bell case where I have my parameter theta that controls the degree of entanglement, transpile it to an ISA circuit, and again, I'll use a set of parameters with 20 different values for theta from 0 to pi. But for each of these values, I'll now evaluate 3 different observables, XX on both qubits, YY on both qubits, and ZZ on both qubits. Now to do this, because I have a shape 20 set of parameter values, I'm going to reshape my ISA observables into a shape 3x1 so that the broadcasting would be a shape 3x20 array. And then when I run this, I'm going to get back my shape pub results. And now for each of my observables I requested to measure, I now get all the different parameter valued expectation values and can plot them as shown here, seeing the XX, YY, and ZZ for each parameter value. So in the examples I used what was called an ISA observable when running with the estimator. Now I'll just take a moment to give a few more details on what it means for an observable to be an ISA observable. So recall that a Hermitian observable for the estimator can be thought of as an operator with a linear combination of Paulis with real coefficients. Now for this operator to be an ISA observable, then it means that each Pauli has to be defined on the same number of qubits as the ISA circuit. So if it was a 27 qubit ISA circuit, each Pauli would have to be defined on 27 qubits. So if you're used to working with abstract circuits and Paulis described on them, such as a 2-qubit Pauli, then to map them to ISA observables, you need to apply the layout of the transpiled circuit to the observables so that they're mapped to the same qubits in the transpiled circuit as your original abstract circuit was. And to make this easier, several of the operator classes in the Qiskit Quantum Info module include an apply layout method that can be used to do this for you, including the sparse polyop and poly operator. So I already used this in the previous examples, but to just go over it again, let's consider a simple case here of a 1-qubit abstract circuit, which I transpile to a backend, a 27-qubit backend here. So that circuit might look like this. In this case, you can see that the transpiler mapped this is the qubit of my abstract circuit to the 4th qubit of the physical backend's qubits. So if I made an observable that was a 1-qubit abstract observable here, given by a linear combination of x plus y plus z, then I can apply my layout to this observable to get an ISA observable, and you can see that it's been expanded to a 27-qubit sparse polyop with identities on all the other qubits, except the 4th qubit where this qubit was mapped to. Now, when you're working with estimator inputs in pubs, you can work with the raw NumPy arrays and observable lists as I've described in my examples, but there are also some helper container classes included in Qiskit that you can use to make this a little easier. So 2 of these container classes are the observables array and the bindings array. The observables array is a NumPy array-like structure that can basically represent an n-dimensional tensor array of sparse polyop observables. And the bindings array is a NumPy-like array object for representing an ND-shaped array of sets of parameter values. And because these are NumPy-like objects, they have convenience methods to do things like reshaping them. And I'll just make a disclaimer that these classes are currently experimental, so their API is not guaranteed to be stable in future versions of Qiskit. So to give an example of what this looks like, I'll import the observables array class from the primitives module, and I can create an observables array that is, I want to be a shape 3-1 list of Pauli's. So I initialize it with a list of Pauli's and use its reshape method to reshape it to shape 3-1. And then it also has an apply layout method, so I can apply the layout to all the Pauli's in this list in one function call and use the circuit's layout as shown here. Similarly, I can import the bindings array to work with parameters. One thing to keep in mind with working with the bindings array is you need to know the names of the parameters, because this is like a dictionary-like object that maps the names of parameters to arrays of values. Next, I'll talk a little bit about how observables are measured on the estimator. So when you go to evaluate an estimator pub with a possible tensor shape of different observables you wish to measure, when running on the IBM runtime primitives, they'll apply some grouping strategies to collect different observables that can be measured together to minimize the number of actual physical circuits with measurements that need to be evaluated. So this is done by collecting all the Pauli terms that need to be measured in all the operators and grouping the Pauli's that can be computed from marginals of a single measurement. So the way grouping is done in the runtime is equivalent to the Pauli list quantum info class's group commuting method with the value of qubit wise equals true. And this will essentially collect Pauli's on different tensor products of qubits that can be measured as a single tensor product. So to take an example where I want to measure 9 different single Pauli's of x, y, and z on each of 3 different qubits, as shown as a list shown here, if I group this, this will be collected into 3 different sets of Pauli lists that can be measured together. So the way the grouping worked here is it collected z on qubit 0, x on qubit 1, and x on qubit 2 that can be measured at the same time, and similarly for the other ones it collected different combinations of the single Pauli's into one group of Pauli's that can be measured simultaneously. So another thing you can use when using the estimator is when computing a Hamiltonian or a more complicated observable that's represented by a linear sum of Pauli's, you can also include the individual Pauli terms to compute the component expectation values when you're running your pub. And because of the grouping, this doesn't actually cost you anything extra in terms of quantum computation to compute the extra measurements. So what this could look like, if I take an example of a Hamiltonian here on 3 qubits where I wanted to measure, say, the average of the single qubit z term on each of the Pauli's, represented here as a sparse polyop, I could construct my observables array to include the Hamiltonian I want to measure, as well as each of the individual Pauli's, which I can obtain from the sparse polyop with its .Pauli's method. And this will be an observables array now with 4 observables in it, given by the sum of the individual Pauli's, as well as each of the individual Pauli's. And when this is run on the estimator, it still can all be measured in a single measurement circuit. Now that I've given an overview of the new API of the version 2 of the primitives, I'm going to be talking about some specific details of IBM's implementation of these primitives in the Qiskit IBM runtime. So the API I've described above allows people to create portable programs that could run on any implementation of the V2 estimator and sampler primitives. Now, when you're running on the IBM primitives, there's some additional functionality which can be enabled and configured by the user using options. And in particular, these can be used to enable error suppression and error mitigation techniques when running on the IBM primitives. So both the sampler and estimator in the IBM runtime support a variety of options, and I'm going to just mention a few of them here. So in the case of the V2 sampler, there's an option to control the default number of shots when running sampler pubs. And some other options that might be of interest are options to control enabling and configuring dynamical decoupling if you want to apply dynamical decoupling error suppression when running your circuits. And also sub-options to control twirling, which allows you to enable and configure automatic Pauli twirling when running your workflows. In the case of the estimator, it has a default precision argument that can be used to set the default precision when running pubs. It also has a default shots argument, which can be used as a proxy for setting the default precision if you're more comfortable working with shots when you run on the estimator. There's also a resilience level option that enables preset defaults for a variety of options related to error suppression and mitigation to enable you to activate certain settings with a single option, which I'll describe more later. And it also supports both dynamical decoupling and twirling, like the sampler. And related to resilience level, there's also sub-options for resilience that allow you to fine-tune or tweak the different levels of error suppression and mitigation through their own options. So now I'll take a little bit of time to talk a bit about the twirling options which were added in the V2 sampler and V2 estimator. So without going into too much detail on what Pauli twirling is in terms of theory, you can think of it as a method of engineering the noise in a quantum device. So when you perform gates in a quantum circuit, they may have noise on them, and a layer of gates might have some complicated noise process that includes incoherent errors, coherent errors, and other sorts of errors. And when you apply Pauli twirling, this is a method of mapping this to what's called a Pauli error channel, which is an incoherent mixture of Pauli errors. Now, how this works in the primitives is it requires some transpilation of the circuits that you wish to run to identify layers of 2-qubit gates that will be twirled or measurements that can be twirled. It will then reparameterize your circuit to add parameters that can be used to inject Paulis into the circuit to implement the twirling. And then it will do some random sampling of Paulis in a special way to be inserted into the circuit that don't modify the output of the circuit but change the form of the noise, that when you average over many different samples of these Paulis acts to implement the Pauli twirling to average the channels to a Pauli channel. Now when you do this with an estimator, it's going to return the expectation values averaged over these different samples, and in the case of the sampler, it's going to return you the single shot measurement outcomes concatenated across the different samples. So the outputs you get in terms of the shape of the expectation values or the bit arrays doesn't change whether you enable or disable twirling. Now twirling can be controlled by a bunch of options inside the estimator and sampler, and now I'll go over a few of them. So first there's an option of whether to apply Pauli twirling at all. So by setting enable gates equals true, you can activate Pauli twirling of 2-qubit gates in your circuit. There's also an option separately to enable measurement, and if you enable measurement, Pauli twirling will be done on all the measurements in your circuit that can be Pauli twirled. And this means measurements that are not used in any control flow or conditional operations in your circuit. There's also options to control the way sampling is done. So by default, Pauli twirling will choose some number of randomization and divide your shots you wish to run amongst them. But you can also customize this by explicitly setting an option to control the number of randomizations when Pauli twirling, and also to control the number of shots per randomization when you're Pauli twirling. Finally, there's a strategy option which allows you to specify how qubits are twirled in the gate layers when the twirling transpilation identifies the 12 2-qubit gates. So what this might look like, there's two ways you can specify options when working with the primitives. So once you've initialized in sampler, for example, you can set options via attributes to enable these as shown here. Or you can initialize the options when you initialize the sampler itself by specifying them as a dictionary like shown here and passing it in when you're initializing the sampler. And as I previously mentioned, if you do not set the number of randomizations yourself, default values will be chosen for you when you enable twirling. And by default, the number of randomizations chosen will be 32. So if you run some number of shots on your sampler, then they'll be divided amongst 32 different randomizations. And if you do set these values yourself, then the product of the num randomizations and the shots per randomization has to be greater than equal to the number of shots you request for those, for all pubs that are run in that run call of the sampler. So the twirling strategy is something new, so I'll go over a bit about the options that are supported there. So when you have a circuit that you wish to twirl, there's a variety of ways you could do this, and this is what the strategy specifies. So there's 4 different strategies supported by the sampler and estimator in its current form. So the first one is an active strategy, and in this case, when identifying layers of 2-qubit gates to be twirled, only the qubits that are active in the gates of those layers will be twirled. So if I take an example like shown here, where I have 3 different layers, each with one CNOT gate, only the 2 qubits in each of those layers will be twirled. So in the first layer, that's qubit 0 and 1. In the second layer, it's qubits 1 and 2. And in the third layer, it's qubits 2 and 3. Now, the next option you can specify for the strategy is active accume. And in this case, it will twirl the accumulated gate qubits up to and including the current layer. So going to this example, the first layer, only qubits 0 and 1 have been used in the circuit up to this point, so they'll be twirled. But when I get to the second layer, it will twirl qubits 0, 1, and 2, because qubit 0 had already been used in the circuit, and now qubits 1 and 2 are used in this layer. And then similarly for the third layer, qubits 0, 1, 2, and 3 will be twirled. The next value you can support is active circuit. And in this case, it will twirl, in each twirled layer, it will twirl the union of all qubits that are used in the entire circuit. So in this case, qubits 0, 1, 2, and 3 are used in the circuit. So for all my twirled layers, qubits 0, 1, 2, and 3 will be twirled. And the final option you can specify is all. And in this case, all qubits in the circuit will be twirled in all layers. So when you're running an ISA circuit, this can include all qubits on the device. So in this case, it was a 6-qubit circuit, and in all my layers, qubits 0 through 5 are all twirled in all layers. Now I'll talk a little bit about the resilience options supported by the V2 estimator in the Qiskit IBM runtime. So the IBM Runtime's estimator supports a couple of different built-in error mitigation methods that you can enable either via resilience levels or individually via resilience options. Now, working with these individual options to turn individual error mitigation methods on and off, you can enable measure mitigation via measurement mitigation option, and this will enable mitigation of the final measurements used to compute expectation values in your circuit. Now, for mitigating errors in the gates of your circuit, there's 2 mitigation methods you can enable. The first is zero noise extrapolation, which can be enabled using the Z&E mitigation option. And the second one is probabilistic error cancellation, which can be enabled by using the PEC mitigation option. Note that these options can't be enabled at the same time. You can only have Z&E or PEC activated, not both. Measurement mitigation can be enabled on its own or with either Z&E or PEC though. So I won't go into details of these error mitigation methods, as they'll be covered in later lectures and tutorials of this summer school. Now, if you enable one of these error mitigation methods, there's additional sub-options you can explore to further control how the mitigation is done. So there's a variety of options that can be used to configure Z&E mitigation, including the type of extrapolation method. The PEC, you can control the number of samples and the scaling. When doing measurement mitigation, this requires learning the noise model of measurements, and there's some options you can specify there to control the way the learning is done. And similarly, when doing PEC mitigation, there's some noise model learning that has to be done, and there's options to control the exact way that is done. Now, while you can use these options individually, if you just want to activate mitigation methods without worrying about the fine details, there's built-in resilience levels that can be used to enable a variety of these options automatically using preset defaults. So there's 3 different resilience levels supported by the estimator. So resilience level 0, which has no mitigation or error suppression applied. Resilience level 1, which enables measurement mitigation and measurement twirling, but doesn't apply any gate mitigation. And then level 2, which has measurement mitigation and twirling applied, as well as gate twirling and Z&E mitigation. And when you enable these, you can also fine-tune them with options after you've initialized the estimator. So for example, if I wanted to initialize my estimator at level 2 to activate Z&E, I could then go in and control the Z&E extrapolator I wish to use, or turn dynamical decoupling on with the options. Now, this is a very high-level overview of the new primitives in the Qiskit runtime. And for additional resources, there's a variety of documentation and tutorials you can follow up with on the IBM website. Thank you.